So we're going to start with lesson 1, which is simply a tuning methodology, a basic introduction into tuning SQL in the Oracle database. We'll define the purpose of tuning. We'll understand the SQL execution cycle. Maybe perhaps you've heard of the terms parse, bind, execute, and fetch. Talk about those steps because understanding those steps is key to being able to tune a SQL statement. We'll talk about the cost-based optimizer, CBO, many people call it, the cost-based optimizer. And then we'll identify the steps in tuning an SQL statement. Purpose of SQL tuning. We want to fix a business problem. Perhaps your overnight jobs are taking too long, report is taking too long, or in an online application, the screen hangs for 5 seconds and people are complaining. You don't want to try to tune something that no one's asked you to tune or you know that meeting your needs. What we want to look for is the best response time. Does the query come back in 1 second or 5 hours? There are other metrics, other things that we can measure, such as I/O rates and CPU usage. But the main thing is response time. And we want to avoid compulsive tuning disorder. DBAs and some developers will spend a lot of time trying to get something to run in 1 second that's taking 5 seconds when there's no business need or business problem that it solves. Response time is the best measure. And watch out for compulsive tuning disorder. Let's get into the SQL execution cycle. So the user process generates the SQL. Perhaps it's ourselves as a DBA or a developer using SQL Developer or Toad or SQL Plus, and we generate an SQL statement. Might be a join of 2 tables. There's those steps that I mentioned before: parse, bind, execute, and fetch. Now, sometimes the order of the steps can change, but this is a pretty common process. And we're going to talk about each one of these steps in a bit more detail in the next slides. Parse, bind, execute, and fetch. Every SQL statement has to go through these processes. Let's take a look at them in a bit more detail. Parse. Soft parse, it's always done. That allows the Oracle database to check the syntax of the statement. Is it syntactically correct? What does the statement really mean? If you say select asterisk from department, it's going to resolve what department means. Who owns department in this schema? Is there a synonym that's pointing to another schema for the department table? So what does the statement really mean? And do you have the permission to access the object that you're querying? Look at this next step, very important. Look at this next step. Search the library cache for a matching statement. Okay, so library cache is a shared memory area. And the library cache is a place where Oracle keeps previously parsed SQL statements. The reason it does that is because if it finds the statement already in the library cache, it does not do a hard parse. And this can save a tremendous amount of time. If it finds it in the library cache, it goes on to the next step. If it does not find it, hard parse. Obviously, this would be necessary on the first execution of a statement. So the hard parse does a bunch of things. Takes some parse locks. Locks is like a 4-letter word. It's a bad thing. Locks decrease scalability. Locks decrease scalability. So hard parse is sort of a bad thing. Then it looks at possible execution plans. What are the different ways that I could execute this statement? In a very simple statement like select asterisk from department, there's not a lot of choices, right? But in a very complex statement, maybe a page worth of select statement, there are a lot of possible plans. And actually, by default, I think the optimizer will look at 2,000 different possibilities. So you can imagine how long it might take to do this optimization. Then it selects the lowest cost plan, and then it stores that lowest cost plan in the library cache. Reoptimization is sometimes done for later execution, but that's an advanced concept that you would learn in the 3-day class. Our general goal is to parse once and execute many times because of the cost of the hard parse, the optimization step, right? So let's parse it once, store it in the library cache, and execute it many times. Parse one, execute many times. Bind. Bind is involved in the use of variables. If you write PL SQL, obviously you've embedded a SQL statement inside that PL SQL. When you write PL SQL and you embed a SQL statement, you often include a PL SQL variable inside the SQL statement. Technically, that's known as a bind variable. What we're doing then in the bind step, or what Oracle database is doing in the bind step, is retrieving the values for the variables from the variables. So it's plugging in real values. This usually occurs after the parse step, which is a bit weird. Makes possible reuse of existing optimized code. Now there is a notion of peaking. The first execution will peak so that the optimizer step that we talked about in the previous slide has an actual value to work with. Of course, the downside of this is that the very first value that you execute with is used to optimize the statement. But the very first value might not be representative of the rest of the values during the life of that SQL statement. So peaking is a pretty good concept, but not a great one. Later releases 11G and 12C of database actually have come up with the notion of changing, adapting the plan over the life of the statement. So it actually can monitor the execution, and if appropriate, it can re-optimize the statement if it finds that it's warranted. Okay, again, a bit of an advanced concept that we would discuss in the 3-day class in more detail. Then, of course, we have to execute the statement. For DML, this is where most of the work is done. I/O from disk. I/O is a bad thing. It's the slowest thing, typically the slowest thing we do in a computer. I/O often involves mechanical motion, and we're moving data from the disk into the buffer cache. There's another cache, a memory area. Buffer cache is a memory area that Oracle uses to store blocks of data from tables. If you re-access that block, Oracle does not have to do an I/O again. And if somebody else needs data from that block, an I/O is not necessary. So there's physical I/O, that's moving from disk, and then there's the notion of logical I/O. I'll mention this again, it's not mentioned on this particular slide. The logical I/O is a read from the buffer cache. A logical I/O is a read from the buffer cache. It means that the data has been moved into the buffer cache, but it's going to be now read from the buffer cache. Or in a subsequent execution, logical I/O may be all that is necessary because the data is already in the cache in the memory area. It's not free though, because there are latches required to do a logical I/O. Notice I said latch, not lock. A latch is a lightweight lock. It does cost some CPU cycles to take a latch. So physical I/O, bad, right? We're going to move data from disk. Logical I/O, we're going to spend some CPU cycles. We're also going to decrease scalability. Latches and locks decrease scalability. So often a way that you make SQL statements run faster is to lower physical or logical I/Os. There's that locks on tables and exclusive locks on rows. Again, you know, this lock thing is a terrible thing to do for DML. If you're doing DML, you're going to be making updates. We're talking about update, delete, update, delete, merge statements. The merge statement, which we'll not have time to talk about today, is a fantastic statement introduced in, I think, 9i, Oracle 9i, which can actually, it's an upsert type statement. It does an update and an insert in one statement, and it really is a beautiful statement and actually can be used to reduce response time of operations greatly. So you should be aware of it. After the execute step, or if you're doing just selects, fetch. So this is where the work occurs for the select statement. And again, there's that I/O from disk if it's not already in the buffer cache or searching the buffer cache. Now there's actually two types of reads that can be done. It's a bit of an advanced concept. An indirect read is a read, that reads into the shared buffer cache. There's latches involved there and all sorts of things because it's a shared area. A direct read copies blocks into the PGA. It does stand for Program Global Area. It's private for a particular user. Everybody gets their own PGA. If everybody gets their own PGA and I read into the PGA, what do you think we don't have to do? We don't have to latch or lock. So we increase scalability. Of course, at the fetch step, we're going to perform joins, aggregations, projections, and so forth. So aggregations might be done with the group by clause, maybe adding a cube or roll up. Projections, fetching back the specific columns we've asked for. So that's what projection means. If you go back to your study of original relational database, projecting is projecting the columns. Select name, address, and phone number from my customer table. So I'm projecting the name, address, and phone number. Of course, we also have to sort the data if we have an order by, and then finally return the result set to the user process. Select statements. We often find ourselves tuning selects, not updates, deletes, and inserts. That's not always the case, but it's more often the case we're tuning selects. I mentioned the merge statement before. Boy, can that be a great way to tune an update and a delete operation. An update and an insert operation. And actually, merge now supports delete, so pretty good stuff. Basic execution cycle for a select statement. Get the rows, do the joins, do some aggregation, project the columns. In other words, get the columns that the query has asked for, and do some sorting. Often requires disk I/O, memory I/O. So we have physical I/O for disk, memory I/O for latches, if we're using the buffer cache, and of course, CPU. So those are the resources, right? I/O, CPU. The work for all this stuff is often done in the PGA, Program Global Area, which again is that private area. Everybody gets their own PGA. Now, let's get to some optimization concepts. Earlier, I said that during the hard parse, that Oracle database can do literally, for complex SQL statements, thousands of different permutations, compare thousands of different execution plans. I think it's 2,000 by default. And the objective is to come up with all these different execution plans and then choose the lowest cost. And here we introduce the term database time. And this is a term that Oracle's been using for several releases right now. So you'll need to become familiar with the notion of database time. And best execution plan means fastest in terms of database time. Well, what is database time? Working plus waiting plus I/O. So let's back into that a little bit. So I/O we know is going to take some time, right? Especially physical I/O. But even logical I/O requires latches, takes some time. We might have waiting. In fact, we'll always be having some amount of waiting for a disk I/O, waiting for a latch, waiting for a lock. Decreasing wait times can sometimes help us, or oftentimes can help us tune an SQL statement. This notion of database time is something that you want to remember and does involve disk, waiting, and working time, actually processing the statement. Now, what we're not accounting for is network time or time in the user process if your client is slow. As I mentioned, there might be better ways to execute a statement, and yep, 2,000 possibilities. These decisions and these different plans, execution plans that the optimizer comes up with are, in most part, driven by statistics, object and system statistics. So, for example, tables are an object. Indexes. So an index is an object which contains pointers to rows in tables. Indexes can help Indexes can help reduce the response time of a SQL statement. Statistics. Object statistics. Object statistics have a huge impact on the cost-based optimizer, and these statistics need to be accurate. So starting a couple releases ago, Oracle actually runs an automatic overnight job or task that collects object statistics for all objects where it's necessary. The DBA needs to keep the object statistics current, maybe by that auto task that runs overnight. There's also system statistics. Oracle collects statistics about your server. How long does it take to do an I/O? On my server, could be different from your server. I'm sure it will be. So system statistics, things like I/O speed and CPU speed, are very important. Size of memory is important too. All of these things come into optimization. There is another optimizer called the rule-based optimizer. It's now deprecated. It was the only optimizer back in the day. And rather than trying to use statistics to come up with intelligent decisions, it simply has some rules. What about these rules? There are the rules. This is the way it used to work. And I'll tell you, once in a while, it's fun to force the turn the rule-based optimizer on. Turning the rule-based optimizer on can sometimes be quite revealing and helpful. But what you're seeing in the rule-based optimizer in these rankings here, what are these? These are access paths. And one of the things that you'll have to come to terms with as you learn about SQL tuning is the different access paths that Oracle has in its bag of tricks. The fastest access path is to go and get a row by a row ID. A row ID is a pointer to a specific row in a specific table. That's the fastest way to go get a row. But who has a row ID? If you go to an index, you can get the row IDs. That's actually what a B-tree index stores is, row IDs. Look at number 4, single row by unique or primary key. That's a query we've all written, right? Select customer where customer number is equal to some number. The rule-based optimizer thinks the worst access path is. It's number 15 in your list, the full table scan. So number 1, number 4, and number 15 should be your first access paths that you come to grips with, if you will. And of course, we study these access paths in more detail in a full class. But getting a row via the row ID, well, where do you get a row ID? Typically, you get the row ID from an index. So it goes to the index first, gets the row ID, and then gets a row. Single row by unique or primary key. We've all written those queries. And full table scan. Select asterisk from department table. No where clause. So it has to do a full table scan, but it hates to do that. It's its last option, even though it might be the best choice. So the rule-based optimizer was not very smart. The cost-based optimizer, on the other hand, is very smart. Chooses the lowest cost plan. Cost represents the expected runtime. Cost is weighted. It's a number that is weighted by I/O time and CPU time. So remember, we said before that Oracle knows how fast your I/O is because your DBA has collected system statistics. I sincerely hope so. And it knows how fast your CPU is. So these are weighted statistics. And the cost doesn't have a unit. It's not equal to dollars. It's not equal to minutes. It's not equal to seconds. It's simply used for comparing different execution plans. We can come up with up to 2,000 different execution plans for a complex statement. It simply selects the one with the lowest cost, the one it thinks it's going to have the lowest I/O and CPU time. Notice that it cannot account for waiting time. It doesn't know how long it's going to have to wait for latches, locks, and I/O. So it relies on accurate statistics. Your DBA must be collecting statistics on a regular basis. The cost-based optimizer rewrites queries to more optimal structures. This is a critical statement. So if you write a subquery, key concept in CBO, query rewrite is a key concept in CBO. You must keep that in mind, because when you look at the exact execution plan, the execution plan may not represent this query that you wrote and submitted for optimization. So if you don't understand query rewrite, how will you possibly understand the execution plan? Here down at the bottom of your slide, you'll notice that it can operate in one of two modes, either all rows or first rows. And typically it's set to all rows. And this is the mode where the CBO is optimizing for the shortest time to complete the entire query. It wants to assume that you're going to get all your rows, so it might do a lot of pre-processing in order to make the total elapsed time or response time of the query low. You might do a lot of pre-processing, like read a table into memory, maybe do a sort, a hash. Another mode, which is not as common but can be very, very helpful, is called first rows. If you set this mode for your session or for your database, the optimizer changes its thinking. Rather than trying to optimize for best overall response time, the optimizer optimizes to give you a row as soon as possible. So typically the optimizer will not choose a plan which does a lot of pre-processing, a lot of hashing or sorting or loading into memory. It simply wants to get you the first maybe 10 or 100 rows as quickly as possible. CBO critical decisions. What are the things that often matter the most to us about optimizing an SQL statement? Join order. Which table should Oracle access first? Whether you're joining 2 tables or 20 tables in a single query, Oracle can only join 2 tables or 2 row sources at once. So what should the join order be? The general rule is you join the small table to the large. In other words, you access the small table and then you access the large table, and your execution plan should reveal that to you. If it's not, this is a red flag to you, folks. This is a red flag. It can have a huge impact on the response time of your query. Critical decisions we're talking about here. So this is the thing you want to hang on your wall. This is the slide you want to hang on your wall when you're tuning. Join method. How should the row sources be joined? Should it do a loop type join, a nested loop? Now I'm starting to talk about join operations. And obviously in our SQL tuning class, we talk about join operations in great detail. Are we going to do a loop join, a nested loop? Or we're going to do a hash join? Which is better for a particular situation? Another critical decision. The access method. Remember we saw the 15 access methods in the rule-based list? And we had by unique or primary key, we had by row ID, which was actually number 1, and the last one was the full table scan. So the access method is a critical decision. How should the filters, a filter is a where clause predicate, and join predicates be implemented? And the general rule is small row sets use indexes, large row sets use scans. Think about that. Select asterisk for my customer table where the state is equal to New York. Well, if only 5% of my customers are in New York and there's this index on the state column, wouldn't it be great to use that index to get that, to solve that query? That's what you want to see in your execution plan. You want to see the index in your execution plan. However, if my query is simply select asterisk from customer, I want to see a full table scan. There's no filtering. So why should I involve an index? It would just slow the process down. Or how about this one? Select asterisk from customer where state is equal to Connecticut. If 95% of my customers are in Connecticut, why would I want to use the index? Go get those customers. Again, it would just slow the process down. I'm going to get 95% of them anyway. If a query is too slow, again, it's a business problem. Don't get into that compulsive tuning disorder thing. What you want to ask yourself is, how is Oracle executing the query? John's going to show us how to do that momentarily. then why is Oracle executing it that way? That can be a big learning curve. Is there a better way? If so, can I tell the optimizer to use it? How can I push? How can I influence the optimizer to use this better way? Maybe it's better statistics. Maybe it's by adding or removing an index. If all else fails, in order to answer these questions, how is Oracle executing the query? Why is it executing? Is there a better way? You must understand your data. You've got to know, for example, that 5% of your customers are in New York and 95% of your customers are in Connecticut. You've got to know that. If you don't understand your data, you're not going to be able to tune your query. And of course, you must understand what your query is trying to do. You must understand, you must understand what the optimizer is doing, what CBO is doing, and why. If the CBO gets it wrong, it's probably your fault. Well, who's your? Your fault. Well, our fault, right? I mean, maybe the statistics aren't correct. Maybe Oracle doesn't know that 5% of your customers are in New York and 95% are in Connecticut. Boy, that's a drag, right? Okay, here's the toughest question of the morning. How do you let Oracle know that 5% of your customers are in New York and the other 95% are in Connecticut? And I have 100,000 customers. Histograms, by the way, are talked about in detail in our 3-day SQL tuning class. And then there are lots of common mistakes that you can make, like putting a function like lower, upper, or toChar on a column that's indexed, but not with a function-based index. So there's lots of common programmer errors. Okay, so we know there are going to be many ways to run a query, typically for complex queries. And we now know that SQL tuning is all about understanding the optimizer, the cost-based optimizer. Gathering information about what's happening, why it's happening that way, testing alternatives, and then pushing the optimizer towards a better execution plan. I want you to look at these queries. Tell me which one of these might be the most efficient. I will tell you that these queries all produce the same result set.